Welcome to the webinar Measurement of Particle Size Distribution using Laser Diffraction. My name is Günther Krolli and I will give you a short theoretical introduction into the technology.
My name is Mike Paluga and I will talk about the practical aspects of determining particle size with our brand new NLZ 22 Next.
Before we now talk about how to measure the diameter of a particle, let's take a look. What does it mean, the diameter of a particle? So here we have two different definitions as an example of the diameter of, in this case here, irregular shaped particle. On the left-hand side, you see the so-called ferrite diameter. We have here two parallel lines touching the particle on opposite sides, and when you now rotate the particle between those two lines, you find a minimum value and a maximum value, the so-called minimum and maximum ferrite diameter. On the right-hand side, a second definition, another definition, the so-called contour hull area equivalent diameter. Here we take the cross-section area of the particle and we calculate the diameter of a circle with an equal area. Of course, there are more definitions of the term diameter, and we always need to keep in mind, okay, what are we talking about? What is the actual definition that we currently use for our measurement? So typically we have some physical properties, or we measure a physical property, and well, this can be, for example, the sedimentation speed of particles in a liquid column, or the attenuation of a sound wave traveling across a sample. And from this measurement, from this physical property that we measure, we then calculate the particle diameter distribution using an appropriate theory, of course. So now the general problem is that when you're using different techniques, you will get different results. Well, the simple reason for this is that, of course, all those theories, they use models, they have assumptions that typically do not fit the reality, and so therefore you have some deviations between the model and the real situation of your measurement. Now, one important factor, as you can imagine here, is the particle shape. So if you have a spherical particle or a totally irregular shaped particle, will strongly affect sedimentation or the scattering of light or any other physical properties that you may observe. Unfortunately, the effect of those different shapes of a particle on the result will not be always the same. So therefore, from one technique to the other, you will see some variation in result. So now let's take a look to some example images of some materials. Here on the left hand side you see electron microscopy images of clay. Clay is a material that typically is measured, or very often is measured, using sedimentation, and sedimentation based on Stokes' equation is of course assuming that particles are spherical. And as you can see here, clay is very flaky and is far away from being spherical, so in principle the result will be wrong. But since this technique is used since many years, everybody relies on those numbers that you create. On the upper right hand side you see, for example, a picture of fibers. Fibers are very difficult to measure in most cases because they hook together. It's different to separate them. You have an extreme shape, they are sometimes bended and so on. So in most cases fibers are really not easy to measure, if possible at all. A simple sample is here on the right hand side, on the lower part of this image. Spherical particles often use a standard material, but that's in most cases quite simple, quite straightforward to measure. Now let's take a look, what actually do we get from our measurement? What is the result that we receive from our measurement? So let's take a look to the situation that we have in laser diffraction as an example. So here on the left-hand side you see a real particle that is illuminated by light, and this will result in an intensity distribution as you see it here in the center of this image. Now we make something what we call a simulation. So we try to generate, or we try to calculate, a spherical particle that gives you nearly as good as possible an identical intensity distribution as what you actually measured. The diameter of this sphere then is what we call the equivalent diameter of laser diffraction. Now let's take a look to the samples that we are looking for. In most cases, particles will generate agglomerates. Particles stick together, and of course in most cases you will not be interested in the size of your agglomerates, but you want to know the size of your separated particles. What means you need to take those agglomerates apart, what we call a dispersion process. As you can see here, maybe it may happen that you cannot take the agglomerate completely apart. Some fraction of the agglomerate may remain, but of course this will be one of the main challenges of the user to de-agglomerate the sample material, to disperse the sample in your instrument or during preparation. So now let's talk about the theory behind laser diffraction, or as we also call it, static light scattering. So here you see the principle of the technique. So we illuminate a particle typically with a laser light, and as already mentioned, you observe an intensity distribution, and from this intensity distribution we then calculate the particle size. Typically small particles will generate large scattering angles, while large particles will create small scattering angles. So that means here the small particles will give you wide diffraction rings, while the large particles give you narrow diffraction rings. And now when you take a closer look to this, and here it is more detailed, calculated the intensity distribution as an example for 3 different diameters, 20, 30 and 40 microns. And you can clearly see here that, for example, the first minimum of this intensity distribution travels from smaller scattering angles to larger scattering angles with decreasing diameter. So in principle, from just the position of this first minimum, you can calculate the particle diameter. Already in this picture you see one of the main problems with the technique is, well, typically you don't have just one single diameter, but you have many different particle sizes. So you have a sample, a wide range of diameters, and all those different diameters of course generate different intensity distribution, and what you get at the end is a superposition of all those intensity distributions. Here already shown with this black dashed line, the superposition of just 3 different diameters. And now the challenge is to calculate from this superposition of the intensities the separate particle sizes and therefore the particle size distribution. What is now the exact theory that we use? Well, here we have 2 different theories. The so-called Fraunhofer diffraction, well, this is valid for large particles. And second, the Me theory, what is valid for both large and small particles. Let's take a closer look to the difference between the 2 theories. So here we have first the Fraunhofer diffraction. Well, as stated here again, valid for large particles. What means large? Well, large here means the diameter of the particles should be larger or must be larger than the wavelength of the light that we are using in our instrument. With our instrument, for example, we have a green laser, so the wavelength is around half a micron. So above half a micron or a little bit more, let's say above 2 microns, 3 microns, will also depend, of course, on the material that you are measuring. But above there, for larger particles, you get reliable and serious results from Fraunhofer diffraction. When we now come down to smaller particles, typically in the submicron range, then you will need to move to the Me theory. The Me theory holds true, as already mentioned, also for very small particles down to maybe around 10 nanometer in this range. The main disadvantage that I need to point to here for the Me theory is that you need optical properties of your particles. For the Me theory, we now need to know the refractive index and the so-called absorption coefficient of the material. That's often not easy to get. Well, in the software of our instrument, you find a database that contains around 2,000 different materials, but often you will have some new materials, some mixtures of materials, and so on and so on. So that makes it often pretty challenging to get correct values. So some people may tell you that with this technique or with their instrument, you can determine the refractive index from the particle size measurement, but that's simply not really true. The lower limit, as already mentioned here, for the Me theory is in the range of 10 nanometer, will again depend, of course, on the material that you are measuring. So black material is a bit better than transparent material, but in general in this range and below there, you then move to what we call Rayleigh scattering. So we'll no longer talk about Me scattering, but about Rayleigh scattering, and then it is no longer possible to really measure the size distribution with this kind of instruments.
So here we see a little gallery of the last 35 years of Fritsch laser particle sizers. You have the first instruments which really look like it up on the left corner, and important to mention would be that this is of course not the real scale, as the newest instrument is of course the by far most compact one of these. And if we have a closer look, you'll see the wet dispersion unit in front. The silver box in the back would be the separate ultrasonic box, and then of course the measuring unit. For the full-blown system, which we see here, we have a measuring range of 10 nanometers to 3.8 millimeters, but then we of course offer a more basic version, which then has a measuring range of 500 microns to 1.5 millimeters. And you can see the according optical setup in a little schematic drawing right here. Of course, this is a little simplified, but what we see is the 532 nanometer green laser, and then the laser beam passes our measuring cell, which, as you can see, is not perpendicular to our laser beam, but is a little bit tilted, and there's a specific reason for that. As for big angle diffraction, we would get total reflection inside the measuring cell glass at an angle of around 48 degrees, but by tilting the measuring cell a little bit to the side, we have the possibility to get scattering angles much bigger than 48 degrees out of the cell glass and still being able to detect them. And the maybe most important part is then our detector, which basically recognizes the light intensities of the not only the scattered light but also the main laser beam. And on the bottom we find a monitor diode where we can also constantly check the laser output power by the reflection of the laser at our measuring cell. And changes that come when we talk about the full-blown version Next Nano would be the additional detectors, which you can see here, especially for the aforementioned big angles. You see 5 detectors up there, which are responsible to detect large scattering angles. And then, of course, for backward scattering, we also have 4 additional detectors, which will then decrease our lower limit to around 10 nanometers. So if we have a look now also at our circulation of the sample within the system, we see there are also 2 possibilities. So the first method would be that we have our wet dispersion unit right here. That's the chamber with the water bath, and the water would be pumped then into the measuring cell through the laser light, out of the cell, and back into the water bath through our pipe, the so-called reflux, where you can also change the position depending on the application you're using it. And then if, in case you have a sample where ultrasonic or ultrasound is needed, then you can just connect the hoses in a way that the water flow goes also through the measuring cell first, then goes back into the ultrasonic box, and from the ultrasonic box back into the water bath. So this would be our sample flow. And now let's have a look at one result. Just as an example here, we have the result of some fly ash measured in an A22. And what we see is basically 2 curves. We have the x-axis on the bottom in a logarithmic scale, as you can see. The distribution here goes from about 0.2 microns to about 200 microns. So we have a factor of 1,000 here. That's also why we need a logarithmic scale to be able to display all our particle size distribution here. And what you can also see is we not only have 2 charts, but we also have 2 y-axes. So on the left hand side we have the so-called Q3, which represents the sum curve. That's this line right here, the continuous line, and it basically tells us at any point of the x-axis what percentage of material is smaller than a certain particle size. On the other side we have the DQ3, or our so-called particle size distribution, which is represented by this bar chart right here, and it basically tells us what kind of, or what amount of sample is within a certain interval, size interval of our distribution. Let's have a look at the theoretical definition of the aforementioned curves. The sum curve, also called the cumulative undersize distribution, is defined as the percentage of the sample volume filled with particles smaller than size x, while the particle size distribution, or also called volume fraction within a size interval, is basically defined as the percentage of sample volume filled with particles within a certain diameter interval. If we now talk about a completely different topic, very important one though, which is most of the time neglected, is sample preparation. Here we have to really stress that this part of measuring particle size can vastly determine the outcome, our results, and thus we have to really take care to make as little mistakes as possible when preparing our samples. So what errors can occur when performing a particle size measurement? Of course, we can have an error during the measurement, a measurement error represented by S measurement right here, but we can also create errors by wrong preparation of our sample, which is here represented by S preparation, and in the end our total analysis error is defined by S, which equals the square root of S measurement square plus S preparation square. So as you can see, the preparation basically can have the same influence on the total error as does our measurement or possible measurement error. And how can we avoid or lower these errors? Let's just have a look on the different error sources depending on particle size. And what we can see if we start with the sampling, which becomes more critical the bigger particle sizes become. Now, why is that? The sampling error basically occurs when we have different particle sizes. And now let's imagine we have a sample with very big particles. So here we would have a lot of volume in a single particle, and now you would get, of course, different particle sizes settling down in different locations of your sample container, wherever you keep them. And now if we just take by chance sample from one locality of this sample container, there would be maybe some particle sizes overrepresented. And here it's very important to do some kind of sample dividing before making a measurement in order to have all different sample sizes or particle sizes represented in your sample. And this error, as you can see, becomes way less critical if we reach small particle sizes. Therefore, once we go into these submicron ranges, what becomes way more critical is the dispersion error. Now, this is, of course, because of the adhesive forces, which are, relatively speaking, much stronger for small particles than they are for big particles. And of course, these forces can lead to agglomeration, which can then give you extremely high errors if you are not interfering here in any kind of way. And last but not least, we have the instrument errors, and that is of course something that we cannot really influence as the applicant or as the user of the instrument. But as you can see, the minimum here is around the range of 1 to 10 micrometers, and this is more due to the optical setup of the instruments, so basically has physical reasons. Let's summarize. Sample preparation basically consists of the sample dividing, which was mentioned, and of course the dispersion. So these are the two main error sources talking about the sample preparation. And we also have two different ways of dispersing a sample, and this is, for instance, the wet dispersion, which we have already shown here in the beginning. But there's also another method, the dry dispersion. To give you a little bit of an introduction into the difference of these two, let's just compare them. So first of all, we have a look at the wet dispersion, and we have already seen this picture before. So with the wet dispersion, we basically have a closed liquid circuit where our dispersion with our sample material is flowing and again and again passing the measuring cell in order to be measured by our laser. And the energy that is introduced in order to properly disperse the sample and minimize our preparation error, in this case, would be, of course, the ultrasonic, which is applied here in the ultrasonic box. The second energy source is, of course, the pump, which basically circulates our liquid through the system. Let's now take a closer look at the dilution of the sample in our wet dispersion, because we have to make a little compromise there. On the one hand, we don't want to add too much sample to get the concentration too high, because then we risk multiple scattering of our laser light within the sample material. So you can imagine that if we have very high concentration, we have a lot of particles within the dispersion, it can happen that a particle that scatters the laser beam, and that scattered portion of light then moves on through our dispersion and gets scattered by another particle, which would be multiple scattering, of course, would give us then a wrong result on our detector, or wrong signal on our detector elements. And so we have to take care to not enter too much sample into the dispersion. On the other hand, we also don't want the concentration to be too low, because then we also risk a very poor signal to noise ratio. So we have to kind of find the sweet spot between these two possibilities in order to get a reliable and good result. The parameter we use to determine the concentration of our sample material within the wet dispersion is the so-called beam obscuration. The beam obscuration is basically the percentage of laser light which is diffracted away from its original path and thus has a direct relation to the sample volume within the dispersion. Here on this graph we have the total sample volume needed as a function of the particle size, and the three colored lines give us three different examples for different beam obscurations. Typically we would look for a value somewhere in the range of 10 to 20%. Now what we can clearly see here is that the amount of sample needed is much higher the bigger the particles become. Finally, let's deal with the dry dispersion just briefly. The main difference between these two dispersion methods is that in the dry way we do not have a closed circuit, but we have a continuous feeding of our sample material, and also the way that the energy is fed into the system in order to de-agglomerate our sample is vastly different, as here we would use air pressure, which is fed into the measuring cell by a turbulent airstream that is generated by a nozzle. And you can compare this to the ultrasonic used in the wet dispersion, as here we de-agglomerate the particles not by the ultrasonic energy but by the particle to wall collisions. And of course you have to also find the right dose here in order to not break your particles if you, for example, have a very brittle sample material. And if we have a look at the schematic setup of a dry measuring cell, you see that we have the sample material flowing in from the top, then the compressed air is coming in from the side. In here we basically have the de-agglomeration process, then the sample is flowing through the measuring cell and the laser beam, and in the end it is vacuumed out by an external vacuum cleaner. So that is basically what I meant by continuous feeding and no circulation. The big difference, of course, is that once you are not able to achieve your desired results this way and you tried everything you can do with the adjustable air pressure, you are basically out of options, as while with the wet dispersion unit you still have the possibility to try adding some catalyst, some tensides maybe into your wet dispersion to further enhance the de-agglomeration process. To summarize the most important features of our new laser particle sizer Analyset 22 Next, we have achieved a very competitive measuring range of 10 nanometers to 3.8 millimeters, while still maintaining a very compact design and also being able to offer a very flexible configuration in order to offer every customer just the features that he really needs. And still everything that we built into the instrument is state-of-the-art, and I really want to stress the wet dispersion unit, which is quite unique in the market. And as I explained in the beginning, the sample preparation, which partially happens within the dispersion unit, is of vast importance in order to achieve good results. And at the end of the day, I think this instrument gives you the best value for money on the market today. Thank you for your attention, and until next time.
If you have any further questions, please feel free to contact us.